Right. So the previous session I seen about Malus law. It says that the cosine component of amplitude will be transferred through the optical crystal. So when any unpolarized light falls on optical crystal, unpolarized light, the cosine component of amplitude along the optic axis. So there will be several components, and out of that cosine component. Let's say if polarized light falls on it, already polarized light falls on optical crystal set at an angle. So if unpolarized light falls, a component of it will be transferred. A component of the light along the optic axis will be transferred, and when polarized light falls on the crystal, which is placed at an angle theta with the incident polarization direction. Let's say the optic axis makes an angle theta with the incident polarization direction. The cosine component of the amplitude, let's say this amplitude is A, and the cosine component is A cosine theta. A cosine theta will be transferred through the crystal. This is A cos theta. So the intensity becomes square of the amplitude. So intensity varies as cos square theta. So what happens actually if theta is 90 degrees, output intensity is 0. No light will pass through it, right? So but if we divide this into several parts, let's say if I divide this into 3 equal parts, like 30 degrees, 30 degrees, 30 degrees. If I divide that 90 degrees angle into 3 equal parts, so then what happens? So I am keeping my first crystal at 30 degrees angle, second crystal 30 degrees from the first one, so that means it will be at 60 degrees, and third crystal is at 90 degrees. So if I keep 3 crystals in series, that means I am introducing 2 more in between. So if I keep only a crystal at 90 degrees, no light will pass through. I am introducing 2 more in between. So what is the outcome? 42% of the light is transmitted. So if I keep only one, so I keep only 30 degrees one, I am removing the middle 60 degrees oriented crystal. So what happens? In that case, 36% of the light is transmitted. So if I keep on increasing the intermediate stages, more light is passing through. So if I split the total interval into steps of 10 degrees, 20 degrees, 30 degrees up to 90, even more than 60% light will pass through. So what is happening actually? So if the crystal is oriented at 90 degrees, then no light is passing through, and if I introduce some other orientations, what is happening? So in the primary stage we consider the crystal as just a window, right? ఫస్ట్ ఏమనుకుంటున్నామండి, ఆల్ అదర్ ఆసిలేషన్స్ ఆర్ బ్లాక్డ్, ఓన్లీ ద ఆసిలేషన్ అలాంగ్ ద ఆప్టిక్ యాక్సిస్ is passing through. That means what? The crystal is acting like a window, right? Only that particular orientation of waves are passing through. So what is happening if I just change the orientation slowly to 90 degrees instead of a sudden 90 degrees rotation? What is happening? So మామూలుగా ఇది ఏమవ్వాలి, if I consider it as a tap and if I just rotate it, if I rotate it suddenly or if I rotate it slowly, at the end of the day water will stop. But what is happening here? If I introduce it suddenly 90 degrees in one shot, no light is passing through. If I vary it slowly, some light is passing through. That means what? There is something missing which cannot be explained on a natural basis. So the basic difference is, it is not the intensity that is passing through, it is the amplitude, component of amplitude that is passing through. So if we have only cos theta, if I is equal to I naught cos theta, in that case, if we vary from 0 to 90, outcome will be 0. మనకి ఫార్ములాలో ఓన్లీ కాస్ థీటా ఉన్నట్లయితే అవుట్కమ్ 0 వచ్చేసేది, ఇది మీరు ఈ 2-3 స్టెప్లు చేసినా కూడా. బట్ బికాస్ ఇట్ ఈస్ వేరింగ్ యాజ్ స్క్వేర్ ఆఫ్ కొసైన్ థీటా, ఆర్ ఇట్ ఈస్ డిపెండింగ్ ఆన్ ద ఆంప్లిట్యూడ్ రాదర్ దాన్ ఇంటెన్సిటీ. ఆంప్లిట్యూడ్ మీద డిపెండ్ అవడం వలన ఈ వేరియేషన్స్ అన్నీ వస్తాయి. ఓకే, సో దట్ ఈస్ ద ఫస్ట్ కేస్ ఆఫ్ జనరేటింగ్ polarized light through transmission. Another one is through reflection. How to generate polarized light? By reflection. So here the controlling principle is Bruster's law. There is a certain angle of incidence. So when light falls on a material, a part will be transmitted and a part will be reflected. That is a usual phenomenon. When light falls on a material, a part will be transmitted, a part will be reflected. So here angle of incidence is equal to angle of reflection. Angle of refraction will be different. Angle of incidence is equal to angle of refraction, usual case. So now, this is the ray model of light. If we consider wave model, if we try to explain the same story using wave nature of light, it adds some more detail also. So what is that? There will be components. So I am representing unpolarized light like this. A component is perpendicularly polarized, perpendicular to the plane. A component is polarized on the plane. Right? So instead of considering all these components, 1000 many components, I consider only 2 perpendicular components. So any point, any direction can be represented as combination of these two. Right? So let's say the oscillations are on a plane, xy plane. Let's say this is xy plane and this is z direction. Okay, so on the xy plane, any point can be represented by specifying two coordinates, x coordinate and y coordinate, right? So, any light wave oscillation can be represented by specifying two components, one along x axis, another along y axis. So that I am representing those two components here, one along x axis, another along y axis. So, I consider this as unpolarized light. Instead of representing all those components, I am representing unpolarized light like this. So now unpolarized light is falling on a crystal. So what happens? A portion will be transmitted. So transmitted components will get separated. So here the polarization components will get separated. So a portion the horizontal vibrations and vertical vibrations, vibrations along x axis and vibrations along y direction will get separated during transmission and also during reflection. During transmission and reflection, those two components will get separated. And there comes a special case for a particular angle of incidence. I call it as a Bruster angle. For a particular angle of incidence, all light with oscillations along y direction, all dot components will be transmitted. Completely. All dot components will be completely transmitted. So the reflected light will have only line components. So for a particular angle of incidence, when I is equal to theta b, all dot components will be directly transmitted. So the reflected part contains only line components. So we get pure polarized light along x direction. On plane vibrations only will exist in reflected light. So reflected light is purely polarized. With oscillations on the plane. That's called Bruster's law. So what happens here is because of this special condition, the angle between the reflected ray and transmitted ray will be 90 degrees because the oscillations are perpendicular to each other. When I is equal to theta b, the angle between reflected and transmitted components will be equal to 90 degrees. So now we use all our rules and regulations. So let's say this angle is R, angle of refraction, angle of incidence is I. So what happens to that R value? What is the value of R? So when I is equal to theta b, I is equal to theta b, this is also equal to theta b, angle of reflection is equal to theta b, and this angle is 90 degrees, then what happens to R? So what will be the value of R? 180 minus 90 minus theta. Right? So this total angle is 180 degrees. Out of that, right? This number is equal to 90 minus theta. Then calculate the refractive index. Right. So in this special case, angle of refraction becomes 90 minus theta. Then what happens to refractive index? It is sin I by sin R, right? What do you get? So this is sin theta b by sin 90 minus theta. It is cos theta b, sin theta b by cos theta b. It is tan theta. Right? So when I is equal to theta b, what happens? The angle between reflected ray and transmitted ray becomes 90 degrees, so that angle of refraction becomes 90 minus theta b and refractive index becomes tan theta b. So if we just know the angle of incidence, then we can calculate the refractive index of the crystal, or if we know the refractive index of the material, we can predict the angle of incidence at which the reflected ray is completely polarized. Right? Let's say if you take a container of water with refractive index 1.33. So refractive index of water is what? It is 4 by 3. 1.33. Refractive index of water is 4 by 3. So what is the angle of incidence for which the reflected light is completely polarized? What is the Bruster angle for water? Let's calculate that. ఒకసారి చూడండి. Theta b for water. ఎట్లా వస్తుందండి? It is tan inverse mu, tan inverse 4 by. What is that number? So what do you get? In radians it is 0.43. 53 degrees, 53 point 1 8 1 3. So if you incident light at 53 degrees to the normal, 53 degrees to the normal, the reflected light will be completely polarized in case of water. Okay, others can be calculated. Radiance length and what is that value of radiance? There is something. Let me check it. That so radiance value is 0.9263 radians. It comes out to be 53 degrees around. Right? So the next possibility of generating polarized light is by double refraction. That is in the next session.